Okay, so we should now be familiar with the determinant of a 2 by 3 matrix. Now we will try and work with a determinant of a 3 by 3 matrix by considering a system of linear equations, so a system of 3 linear equations in 3 variables. So let's say we have a system like this. So we have this following system. As you can see, there are 3 linear equations and they are in 3 variables, x, y, and z. All of these are the coefficients of my variables, and these are just also constants. So we have this system of linear equations, and if I were to solve a system of linear equations like this, for a system like this, I can also apply Cramer's rule, right? I can apply Cramer's rule to solve this kind of a system, given the fact that the determinant of my coefficient matrix of this system is not equal to 0, right? So let's consider the coefficient matrix of this system. So in my first column, I will just consider the coefficients of my x variable. I will have a11, a21, a31. Then the second column will be the coefficients of my y variable. We will have a12, a22, a32. And then finally, for my third column, I am considering the coefficients of my z variables. So I will have a13, a23, and then a33. Right, so this is my coefficient matrix A of this system, right? Now, if I were to apply Cramer's rule, then I would have to consider the determinant of this matrix A, right? So the determinant of the matrix A. So we have the determinant of this 3 by 3 matrix, right? This is a 3 by 3 matrix. So we have the determinant of a 3 by 3 matrix. Now, how can we evaluate such a determinant? We know how to evaluate the determinant of a 2 by 2 matrix, but what about this case? Now, in order to evaluate this first, we have to understand what the minor of a matrix is, as well as the cofactor of a matrix, right? So what is the minor of a matrix? Let's say that I'm considering this entry here. I'm considering the entry A11, right? Then the minor of the entry A11 can be denoted as M11. We can denote the minor of an entry of a matrix as capital M with the subscript 11. And we can find this minor by eliminating all of the entries of the row and column that this entry is on. So this is on the first row and first column. So if I eliminate the entries on the first row and then the first column, I am left with these entries, these 4 entries, right? So the minor of A11 will just be the determinant of the matrix that contains these entries, right? So the minor of this will be the determinant that contains these 4 entries. I will have A22, A23, A32, and A33. Right? This determinant, this is the minor of A11. Right? If I consider the entry A12, then the same process occurs for the minor of A12. So M12. This is going to be equal to. So if I eliminate the row and column that this entry is on, so this is in the first row, second column, I'm left with these 4 entries, right? So this will be just the determinant that contains those entries. So I will have A21, A23, and then A31, A33, right? If I were to consider instead A22, this entry, then the minor of this, so M22, the minor will be, I will have to eliminate this second row and this second column, right? And I will be left with A11, A13, A31, A33. So I will just have the determinant with these entries A11, A13, A31, and then A33. And we know how to evaluate determinants of a 2 by 2 matrix. So this should be easy to do, right? So these are the minors of the entry of a matrix. So these are the minors of the matrix A, right? So we can denote the minors of an entry Aij as, so the minors of the entry Aij of some matrix A can be denoted as Mij, right? So these are the minors of the matrix A. Now, what about cofactors? Well, we can denote the cofactor of a matrix as capital A ij, right? So the cofactor is defined as follows. So we will have -1 to the power of I plus j times the minor of the entry that we're considering. So we're considering the entry Aij. This is our entry that we're considering, and the cofactor of this entry is given like this. So we are multiplying -1 to the power of I plus j with the minor of this entry. So we have Mij, and this is my cofactor, right? So, for example, if I go back to my determinant of the coefficient matrix, if I were to consider, let's say, A12, this entry, the entry A12, then the cofactor of A12, which we can write as capital A12, this will be equal to, so A12 will be equal to -1 to the power of I plus j. I is this subscript and this is my j, right? So I will have 1 plus 2 times the minor of the entry A12. So the minor of A12, right? So what is the minor of this? It will be just this determinant. We will have A21, A23, A31, and A33. Right? This is going to be the minor of A12. Right? We eliminated this row and this column. So that is how we find the cofactor of the entries of a matrix. Now, how do I evaluate such a determinant? What I can do is I can just multiply each entry in a row or a column by its cofactor and then sum everything together. And that is known as expanding across a row or expanding across a column, right? So I can expand across any row or any column of this determinant. Let's consider the first row. Let's expand across the first row to evaluate this determinant. So what will I do? I will multiply each of these entries in this row by its cofactor. So let's start off with A11. So I have A11 times its cofactor. So times A11, right? And this is just equal to -1 to the power of 1 plus 1, since this is ij, times the minor of A11. That will be given as A22, A23, A32, and A33. And then I move on to this entry A12. So then I have plus A12 times its cofactor. So I will have -1 to the power of 1 plus 2 times its minor, times the minor of A12. So I will have A21, A23, A31, A33. And then finally, I consider the last entry here, A13, times its cofactor. So I will have -1 to the power of 1 plus 3 times the minor of this entry. So the minor of this entry will be these 4 entries here. So I will have A21, A22, A31, A32, right? So if I work this out, I will end up with, so this will be just equal to, I will have A11. So this portion here, right? So if I go back, this portion here, this will be +1 when this power here is even, right? And if this power is odd, then this will be -1, right? So in this case, we have -1 squared. We have plus A11 times A22, A33 minus A23, A32. Then we have this term here, -1 to the power of 3 So that is an odd power. So we have minus A12 times A21, A33 minus A23, A31. And then finally, we move on to this. We have A13. This is positive 1. So we have plus A13 times A21, A32 minus A22, A31. Right? So this is how we evaluate the determinant of a 3 by 3 matrix. Now, in this case, we expanded across the first row, but that is not the only way that we can evaluate this. We can also equivalently expand down the second column, for example. We can expand down the second column, right? So we can expand across any row or down any column. So we're considering now the second column. So we apply exactly the same process. So we consider A12 times minus 1 to the power of 1 plus 2 times the minor that we get, which is A21, A23, A31, A33. Then we move on to the second entry of this column. We have plus A22 times minus 1 to the power of 2 plus 2 times the minor of this entry, right? So I will have which entries remaining if I eliminate this row and this column. I will have these 4 entries remaining, right? So I will have A11, A13, A31, A33. And then finally, if I move on to the final entry, I will have plus A32 times minus 1 to the power of 3 plus 2 times this entry, these entries. The determinant will have these entries. So I will have A11, A13, A31, and then A33. So in this case, what we did is we expanded down the second column to get this. And we just have these determinants of 2 by 2 matrices, which we can evaluate very easily. Now, as you can see, these determine whether we have a positive sign in front of our entries or a negative sign, right? So this portion of my cofactor, so this entire thing, this is actually just my cofactor of this entry. So this is the cofactor of A32, and this is the cofactor of A32. This entire term, this is the cofactor of A22, and this entire term is the cofactor of A12, right? And this portion here, this portion, minus 1 to the power of I plus j, this determines whether the cofactor is positive or negative. Now, there is a very quick and easy way to remember when we get a positive sign or a negative sign. If I'm considering a 3 by 3 matrix, then the first entry will be positive, then we will have a negative sign, then a positive. If I go down each column, I will have minus, then plus. I will have plus, then minus, minus, then plus, right? So after each entry across a row or column, the signs are constantly interchanging, right? Now, if I extended this to a 4 by 4 matrix, then I would carry on once more. I will have minus, plus, minus, minus, plus, minus, plus. So this is for a 4 by 4 matrix. So we can quickly remember the signs of a cofactor using this method. So now let's go back to the system that I started off with. So we started off with this system of linear equations. And as you can see here, this is just the determinant of the coefficient matrix that I get from this system. Now that we know how to evaluate the determinant of a 3 by 3 matrix, we can apply Cramer's rule to solve such a system, given that this determinant is not equal to 0, right? So we can also represent this system of linear equations as this column vector in 3 dimensions multiplied by the coefficient matrix A, and this will be equal to D1, D2, D3. So we can also write a system like this as follows, right? And if the determinant of A is not equal to 0, then we can apply Cramer's rule to find the values of x, y, and z, to find a unique solution for this system of linear equations. So similar to the system of two linear equations of two variables, to find x, we will have in the denominator just the determinant of a, and in the numerator we will have this exact determinant, except the only difference is we will replace the first column with this column on the right hand side. So we will have d1, d2, d3, and then we will have a12, a22, a32, a13, a23, a33. So as you can see, the second and third column remains the same except the first column. The first column just gets replaced by this vector here, this column vector, for the case of x. Similarly for y, in the denominator we once again have the determinant of a, and in the numerator this time we replace the second column with d1, d2, d3, and the first column will just be as usual a11, a21, a31, and the third column is also the same a13, a23, a33. And finally for z, we will also have the determinant of a in the denominator, and in the numerator we replace the third column. So we have a11, a21, a31. The second column remains the same. We have a12, a22, a32, and in the third column we have d1, d2, d3. Right? So using this, we can find a unique solution for this system of linear equations in three variables. Right? And this is the Cramer's rule for a three-variable system with three linear equations. Right? So if the determinant of a is non-zero, then our system has a unique solution. We will get a unique solution. Now, one thing we should keep in mind is that if I have the determinant of a 3 by 3 matrix, let's say a1, b1, c1, a2, b2, c2, and then a3, b3, c3, for a determinant like this, if any row or any column, if all the entries of any row or any column is zero, like this, if all three entries of a column or a row is zero, then the determinant of this will be equal to zero. This will be equal to zero, right? Similarly, if the entries of a certain column were zero, and this was b3 and c3, then this would also be equal to zero. So for any matrix A and for any vector C, if the determinant of A is not equal to 0, then we will have a unique solution V such that AV is equal to C. Right? This is my unique solution. And just as a reminder, I should also mention that if the determinant of a matrix is equal to 0, then A is a singular matrix, and if it is not equal to 0, then A is non-singular. So a system like this, where AV is equal to C, this will have a unique solution. So we will have a unique solution if A is non-singular.